Hello everyone. We today start new topic, which is called set theory. Right here. Set theory. This is chapter 2. The set theory is the base of the whole mathematics. The most difficulty part of that one for you is new words, new ideas, and new combinations. Okay, so it's not like arithmetic and algebra or whatever. It's absolutely different but very understandable. So that's what I want you to understand. Now, it consists of 4 parts. The first part is called symbols and terminology. Second part is Venn diagrams and subsets. The next one is set operations, and the last one is surveys and cardinal numbers. Okay, actually, this is one whole thing which you must learn. So if you have, because you have your papers, please open chapter 1, okay, 2.1. Okay, I put all these papers on the D2L so you can see them at all. Okay, now we start with symbols and terminology. Symbols and terminology. So let's start first with the definition. What is a set? A set is just any collection, whatever. So, for example, if we consider my class, this will be set of students, okay? Or if I consider desk, computer, and videotape, it's a set of 3 objects, and so on. Some sets are finite, contains only finitely many numbers. We can count 1, 2, 3, 4, 5 up to some number. Some of them are infinite, like natural numbers, real numbers, and some other quantity. Okay, so we start sets. Okay, as a description. Okay, there are 3 methods to design the set. Okay, first one is word description. And I give you a couple of examples. Word description. For example, the set A of all students okay, or so for example the set of 5 first counting numbers. Or, so this is on the second one. Or, say, the set of all acute triangles, and so on. You understand that, right? Usually the set here, if I use word description, I describe the homogeneous kind of set. So all students So I consider students. Here is the set of first counting numbers and 5 first numbers. The set of all acute triangles. So I consider acute triangles. And usually the word all, when I say all, it means that I consider all objects with that property. Usually, so here I omit word all. The set of A of all students. And let me just write the set B of the, let me just write the 5, okay, A, B of the 5 first counting numbers. Or the set C of acute triangles. This is word description. Clear? Just I describe. So the set of objects, and I said what objects I am talking about. Okay, second one is the listing method. So here let's write capital E description. Okay, listing method. Instead of describe this set with words, I can just draw this draw like a picture, or just write them in one parenthesis. So, for example, the first A could be written as follows. I write parenthesis, and then I just write the first object, second object, and so on. By the way, so I need to say immediately that objects of any set are called elements. Elements of a set. Instead of saying object, I will say element. So set is the collection of elements. Collection, or just a union, or whatever. Collection. Collection is the best word. So how would you write the first one? The set A of all students. I just write student number 1, but with the name and first name, last name, and so on. Okay, student number 2. In this case, elements are students. This is first element, second element, and so on. And student number n. Okay, some student. And then I close the curly brackets. Clear? So for example, okay, right now I see 2 students, so I write your name and then your name. It will be a set of 2 students. It's in words. But if I want to write in the listing method, I call student, okay, your name, and then comma or semicolon, okay, and your name. Okay, next, so for example, B. What is B? Could you tell me? The 5 first counting numbers. What is the first counting number? Or integer, or a whole number?
1.
Yeah, 1. 2, 3, 4, 5, that's it. Okay, which description do you like better? That one is clear, right? Immediately you see, and you see this 1, 2, 3, 4, 5, the numbers are elements. And this is the description. Okay, and next one, C, is all acute triangles. Okay, and here I just write, there are infinitely many such triangles. What do you know? What is that acute triangle? Acute triangle is,
It's underneath 90 degrees.
yes, each angle is less than 90 degrees, right? Okay, so okay, triangle number 1, triangle number 2, and so on. Actually, it's infinitely many. Let me just write infinitely many. Infinitely many triangles. Okay, by the way, so I think this. Okay, but there is the third method, which is the most important for us, and I have to erase. Here. Okay, number 3, the third method is that's what you have to learn. That is clear, right? Description, this is just, we just call each element separately. Okay, now the third method is called self-builder. Okay, what is that? Instead of saying about all elements, I describe only one element. And after that I say elements such that, and they have some property. For example, let's write number, that one, number 2 in that self-builder method. So what is A? Okay, now that one is very important. I write the following. A is, and then I write X or whatever other letter, or Y or Z, okay, or small a, or a letter of a Greek alphabet, whatever. Okay, so first letter. Then after that I write vertical bar. Vertical bar means pronounced as follows. It's, let's write such that. Okay, so X such that, and after that I describe what is that. Okay, in the first one, what is student? Such that X is a student. Okay, then I close the parentheses. Got it? So I describe only one student and said it. And when I write parentheses and write X, it means all X's after that such that, and that one X is a student. Okay. So this is a self-description, self-builder. It builds itself. So X, I take X, what is that? Student. Who else? Another student, another student. So and so on and so on. So we have student number 1, student number 2, and so on. Now what is B? Okay, all X's such that X either 1 or 2 or 3 or 5, right? And then I write the following. X is a whole number from 1 to 5. Okay, and after that, so this is self-description. I take X, and I see that X is a whole number from 1 to 5. So for example, if I take X equals 1, therefore it will be 1, first element. If I take 2, it will be 2, 3, 4, 5. Okay, so that is the second one, and now C. Okay, let me just now use letter delta, as I used before, delta, such that delta is an acute triangle. Okay, so you see n, I describe a single element. But when I wrote delta here and then vertical bar, it means delta, elements delta, such that, and now I describe what is that. Delta is an acute triangle, and after that I say that we consider all such deltas. So this is the same as what I erased, all triangles with all acute angles, less than 90-degree angles. Okay, maybe I have to, okay, got it. So you see, and now I want to give you some examples, and we will work, you answer the questions. Okay, let me erase everything here, and we have to go from one description to another description. You have to understand the description in okay, in the three possible ways. Okay, so now I will ask you some questions and you answer and we will work together. So first, all x's, okay, so such that x plus 5 less than 19, comma, x greater than 10. Okay. What is that? Okay, x, okay, when I write inequalities, it means x is a number. It's not necessarily integer. Okay, I didn't say anything. The only restriction is that one and this one. Let me write this as follows. All x's such that if you subtract 5 from both parts, you'll get x less than 19, and then comma, and x greater than 10. Comma means and. This property and that property. You see, here we have a bridge, a connection with logic. So logical and. Okay, so what is that? Equals all x's such that, and let me write this as follows. X greater than 10, right, first, and then less than 19. So what do you see? Now that one is the best form. All x's such that x greater than 10 and less than 19. What is that? If you draw a line and mark point 10, mark point 19, you have to consider all possible x's between them. So just put any point to the x. This x is described here. X satisfies that condition. And I consider all such x's. All such x's which satisfy that condition. Got it? So what is that? Between 0 and 10. 10 is not included because it's strict inequality. 19 is not included, so it's by the same reason. So therefore I have to draw parentheses, left parenthesis, right parenthesis. And consider all possible points, all possible numbers between 10 and 19. What is that? It's called open interval. Why open? Because 10 is not, the end does not belong to it. 10 is not considered. And 19 does not belong. But all the points closer to that, as close as you want, they belong. So therefore the answer is open interval. Interval 10, 19. Means from 10 to 19. Got it? Okay, now I ask almost the same questions, but the answer will be drastically different. Okay, I write the same thing, x, such that x plus 5 less than 19, x greater than 10. And make one more condition. X is, so I write, instead of is, I write equals. Is an integer. So therefore, if I make the same transformations, I'll get the same inequalities. All x's such that 10 less than x less than 19, and one more condition, x is an integer. Okay, so what I have to do? I have to take, so if I forget about the second one, it's integer. It will be an interval. The same interval as before. From 10 to 19. But now it's an integer. Could you tell me some integer between 10 and 19? 11, good. Next, 12. Next, 13. Okay. Let me just write. And what is the last one? Is 18. 19 does not belong because it's strict inequalities. So therefore, that self-builder description I can rewrite in the listing description. So what is that? It's just 11, 12, 13, 14, 15, 16, 17, 18. A little bit later, I will ask you how many elements are in that set. If you write this way, you cannot find that. But if you write as a listing, in the listing condition, then you can find. Actually, what is that? It's arithmetic sequence. That's why I taught you arithmetic sequence. How many numbers are here? 18 minus 11 plus 1. 8. And let's count. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Maybe I tell immediately. The number of elements. Okay. Number of elements. Okay. How do we call this set? Let's call this set by D. Okay. Number of elements in D is denoted in two different ways. One way is like in the book, it's n of D. Okay, it's clear, number of D. Another way is just absolute, kind of absolute value of D, just vertical bars. How many elements? And what is the answer in this case? 8 from 1. Okay, 8. So if I ask you the question, what is the number of elements, you will tell 8. And let me tell you immediately the name of, instead of saying number of elements in D, we'll say another word. It's a new word we have to use. It's called cardinality. Cardinality of set D. Cardinality of set D is the same as the number of elements. So cardinality of set D, and then after that you write n of D, or absolute value of D, and the answer 8. Got it? For example, if I ask the same question about number 1, what is the cardinality of that set? It's infinitely many. So therefore the answer will be infinity. You know how infinity is written? So let's suppose this set is E. Cardinality of E is infinity. But actually in the set theory, maybe it will be in the very last lecture, I will tell you that there are different infinities. Some infinity are countable and some are uncountable. Okay, but this will be much later. Okay, let me show you some more examples. Okay, it's clear, right? So I can erase. Okay, let me erase. And now I ask a question, and you will answer me. What is the set and its cardinality? Okay, so number 3. Okay, I describe again all x's such that x is divisible by 5. Okay, let me just try. Divisible by 5. Okay, that is notation. Got it? 3 dots. Okay, first of all, this one. X is an integer. Okay, next, x is greater than 1000. And finally, x less than 1005. Maybe I just try this one. Less than 1006 first. Okay, so what is that? We have to find all x's, which are first of all integers, divisible by 5, greater than 1000, and less than 1006. Okay, do you know how to find if a number is divisible by 5? You have to look at the right end, the rightmost digit. If it's 0 or 5, then it's divisible by 5, like 15. 5 is the last digit, or whatever it's written before it. If the end is 5, it's divisible by 5, or 0. Only the only possibility. So, what is that set? Call it S. So S equals, now let's write in the listing form. Could you tell me what is that? So the number greater than 1000. 1000 doesn't work. If I wrote greater or equal, then it would be 1000. But I wrote strictly greater, so 1000 doesn't work. 1000 does not belong to this set. Clear. Okay, let's look. Next is what? 1001. Divisible by 5? No. 1002? Not. 1003? Not. 1004? 1005? Yes. Okay, let's write 1005. And next, but actually, by the way, look, x less than 1006, it means we count until 1005. And this is the only one number. So therefore, you see that long description, actually, if you look thoroughly, you will see that set consists of only one element. So you can write, okay, this is logical conclusion, n of s equals 1. It means one element, and this element is equals 1005. Clear? Okay, but now my initial problem was the following. Let me just write S prime. S prime is just the same letter, but to distinguish S prime from S, I write prime. Okay, I write the same thing. X is divisible by 5. X is an integer. X greater than 1000. But this time, okay, let me erase that one. Let me and write x less than 1005. If you start looking, what is that? Integer divisible by 5 greater than 1000. 1001, 2, 3, 4, and then boom, that's it. 1005 does not belong to it. So what is that? How many elements is here?
None.
None. Let's write n of s prime. None means 0. Okay? So that set doesn't have elements at all. There is only one set with no elements, and it's called empty set. Empty set. And it's written like 0 and then crossed. Empty set is a set. Now let me just write only, because it's only one, I will write this set. Is the set with no elements. So this set doesn't have elements at all, so it's empty. All empty sets are the same empty set, and but descriptions could be different. For example, what is the set of all fishes, all speaking fishes? 0. Zero what? 0 elements, no elements. So it's empty set. Empty set. Or like all people, say German people who doesn't speak German. It's empty set, so all of them speak German, right? So no such an element who does, people who do not speak German, people who do not speak German. Okay, so you understand what is empty set. Okay. Now let me show you a couple of more examples, and now you will tell me maybe more sophisticated. Okay, so x, and let me call it A, B, C, D, so this is set A, x such that x squared less than 0. Okay, what is that set? Tell me at least one element of this set. So give me a number whose square, you understand what square, it means multiply by itself. The number so that the product by itself will be less than 0. So say if you take positive number multiplied by itself, you'll get a positive number. But if you take negative number,
The x will be negative.
no. Say negative 3 times negative 3. Minus times minus is positive.
Yeah.
So therefore it will be the same as 9. Plus 3 times plus 3. positive. It's also 9. So therefore, you see, if this is x squared, okay, then you cannot say that the x equals 3. It could be also negative 3. So if x squared equals 9, then we conclude that x equals 3 or x equals negative 3. Because both of them, if you take 3 squared, you get 9, negative 3 squared is 9, right? But you see, and if you take, for example, x squared equals 0, then what x? Which number multiplied by itself gives 0?
Just 0.
Just 0. And it doesn't matter. Plus 0 or minus 0 is the same. 0 is neutral element. Okay, but what happens in this case? You understand that, right? So what is that set? X squared, either positive or 0. Right? So therefore it cannot be less than 0. So whatever x you take, the square root will be greater than 0 or at most equals 0. Cannot do less. So the answer is empty set. This set doesn't have elements. But suppose I write the following: b all x's such that x squared less or equal than 0. Okay, less than 0 it cannot happen, so it's equal to 0. It is the same as all x's such that x squared equals 0. And you can write, if you write this set, you'll get just only 0. So x equals 0. In this case, b has exactly one element, which is 0. Clear? Okay, good. One more things. Okay, so say c is number c such that c is a digit. Okay, how to write it in the counting way? What are the elements? You have to convert that sentence into descriptional sentencing. You have to write in elements. So is a digit. So what digit could be? Could be 0, right? Could be 1. Could be 2, 3, 4, 5, 6, 7, 8, and 9. This is by definition is a digit. So if I say that c is a digit, and here I wrote all c such that each such c is a digit, I have to describe every single digit. And now you see that n of c, the cardinality of c equals 10. You got it? If I ask you that question on the quiz, you will answer. What is the cardinality? Got it? Understandable? Okay, again, c is the set of all small c's such that small c is a digit. So therefore, you think, what is a digit? Digit could be from 0 to 9. So c could be 0, could be 1, could be 2, and you have to describe, and we describe all digits satisfy that property. So it will be this one, and the number of them is 10. Now let me give you a more complicated question. D is a set of all these such that D is a 2-digit. You see, I described only one integer, and I say that if D is in here, if some element is in here, it must be a 2-digit integer. So what is the description? It will be 10, 11, finally 99. All of those. Now, what is the cardinality of D? It's arithmetic sequence. Yes, 99 minus 10, then divide by 1 because the difference is 1, right, all the time. but let me omit this. And after that, plus that 1. So the answer is 89 plus 1 is 90. Okay, cardinality is 90. Okay, got it? Got it, right? So that's what you have to write. So one more, maybe one more. E. Okay. X such that x is even and x less than 13, even counting number. Even, oh yeah, counting number. What is that? So what is so therefore it should be counting. 1, 2, 3, 4, 5 and so on. This one property, counting number. Second, it must be even. Even is divisible by 2. Okay, 2, 4, and so on. By the way, okay, so let's write 2, 4, 6, 8, 10, and 12, because it's less than 13. Next restriction comes in force. You see, if you see counting number, what is counting number? Numbers which I can count, 1, 2, 3, and so on. But if instead I will write, instead of counting number, if I write integer, integer is a little bit different thing. Counting number is a whole number, okay, 1, 2, 3, and so on. Integer means it could be 0 and also could be negative. So therefore in this case, and let me just write positive, not positive, non-negative. Non-negative integer. It means non-negative, it means cannot be negative, but could be 0. So question arises, can I write 0 here or not? Is 0 divisible by 2? Is 0 an even number?
No.
Okay, that is tricky question. So not tricky question for those who doesn't know that, but actually see. Question, is 0 an even number? Or maybe odd number? Or maybe both? Or maybe neither? What is the correct answer? You have to divide 0 by 2. If you divide 0 by 2, what you get? 0. So it's divisible by 2, right? Number divisible by 2 is even. So 0 is even. Is it odd? No, it's not odd. Odd is a number when you divide by 2 gives a remainder, 1. But it's not that. If you divide 0 by 2, you'll get 0. So it cannot be even or odd, and odd simultaneously. So therefore the answers odd is incorrect, neither is incorrect, either 0, okay. So the only correct answer is 0 is even. Okay, let me just write the following, maybe a little bit more interesting description. Okay, so consider the set. Okay, just write f to n such that n is a whole number. Now, what is whole number? Let me just write the set of whole number, so W. Okay, whole numbers. The set of whole numbers. What is that? Also, let me just write these whole numbers, and then I write the following. N and B I just write that way because it's set. N is natural numbers. natural numbers. Now, natural numbers are counting numbers. 1, 2, 3, 4, and so on up to infinity. So the cardinality of this infinite. Whole numbers almost the same, but 0 is added. 0, 1, 2, 3, and so on. So if I say n is a whole number, it means that n are taken from this set. N is taken from this set. But, but here it's written 2n. So I'm describing the number 2n. So for example, if I take n equals 0, 2 times n will be also 0. Now if I take 1 here, 2n will be 2. Okay, and so on. So let me just write down what I will have. I will have 0. Then if n equals 1, then 2n, which I described 2n. So it will be 2, okay. If I take n equals 2, plug it in here, I'll get 4. It will be 4. Then I plug in 3, it will be 6. And so on. And what do you see? All integer, so all even numbers. So therefore, what is that? It's even numbers. Okay, I didn't write the set of even numbers. Actually, the set of all even numbers. And you see 0 is in here. So therefore, usually for brevity in mathematics, people write, consider the set 2n, and without any description. The only what they can write that n is from the whole numbers. Then it will be even numbers, but also not only that one, but also positive, non-negative. Positive for those and 0 for this one. Okay, got it? So all even numbers are described as follows: 2 times n. 0 is 2 times 0, so it's even. 5 is 2 times 2.5. It's not even because n must be a whole number, but 2.5 is not a whole number. 2 times 2.5 is 5, but 2.5 is not an integer. That's why the product is not that one. Okay, I introduced 2 infinite sets, but now I introduce also a very important set, which is called Z. Z is the set of all integers, both positive, negative, and zeros. So I write 0, and I write 1 here, minus 1 here, 2 here, minus 2 here, 3 here, negative 3 here, and then I write dot, dot, dot. It means that it goes to the negative direction indefinitely. And then I write here dot, dot, dot. It means I go to the positive direction also indefinitely. And the picture of that is as follows. You draw a line, you mark 0, which is called origin. Let me just draw 0. And then you mark 1, 2, 3, okay, so on, and you draw the arrow. That is positive direction. So it goes to plus infinity. And if I draw the line in that direction, I mark negative 1. Important point is this one. It's just the origin. We just write origin. Negative 1, negative 2, negative 3, and so on. You have a grid. Infinite grid in both directions. Now let us look what are the other sets. 1, 2, 3, 4. So if I draw the line, 0 I cancel, so this will be 0. And then I have to mark 1, 2, 3, and so on. So therefore, if I compare these two sets, that set has infinitely many elements in both directions. N has only this one, so N is that part. Okay, if I go only from this point, this will be N. Okay, now what is whole numbers? Now this time I must include 0. 1, 2, 3, okay, and so on and up to infinity. And you see that I add 0, and I have a little bit bigger set, which is called what is that? Yes, whole numbers. Right. So therefore, a set of whole numbers contains the set of natural numbers, and but is contained in Z. Okay, this is written as follows. I will just introduce that, but it will be special notation later. I will write this as follows. Set Z includes, okay, that sign is includes set W, and that set includes Z. So you see that line, it contains W, and W contains N. Oh, sorry, no, it's here, N. You see? So that is the smallest set, this is the bigger set, one more element is added, and this one is the biggest one. Okay, so now you understand how to describe sets. Okay. There are many different things, and maybe I will write a list of sets. For example, different examples. For example, let me just write. Okay. Okay, 1 over n, such that n is an integer. Just write a positive integer. Is a positive integer. So what is that? How to write in the listing form? So n equals 1. It will be 1 over 1. I plug in for n, positive integer. Next is 2. I just write 1/2. Then I write 1/3. Then I write 1/4, and so on. You got an infinite set. A set fractions whose so how to describe it in words? All the fractions with the numerator 1, and in parentheses, and denominator a positive integer. Positive. You see how many words I used. Instead of that, I just throw this one or decipher and got that set. Okay, all the sets could be described this way. Besides these sets, I can introduce one more set, which is important for, so it's described in the book. And so consider the following. It's denoted by Q, like that, Q. It's a standard notation. Okay, this is all, let's write P over Q. So therefore, what do I describe? I describe fractions. P over Q, where P is a positive integer. Then just write, no, just an integer. And Q is positive integer. Okay, remember that Q cannot be 0. You cannot divide by 0. You can divide 0 by something. 0 divided by anything will be 0. But you cannot divide 1 by 0. It means how many zeros you have to add to get 1. Okay, it's impossible to do. Add 0, 0, 0, 0, 0, add. You will never get a 1, right? But if you take 0 divided by 1, how many times you have to take 1 to get 0? None. That's why it's 0. Got it? Okay, so what is that? If you write, for example, p equals 1 and q is equal 3, or just take 2 and divide by 3, or take negative 5 and divide by 7, or negative 5 and divide by 3. Okay, all possible, so it's infinitely many of those. Okay, so it's called Q, and there is a special name for such a set. So this set is important. It's called rational numbers. Rational, okay, set of rational numbers. So therefore, a rational number is a fraction whose numerator and denominator are integers. Okay. For example, how about 5? Is it a rational number? Is it a fraction?
No.
Can it be represented as a fraction?
Yes. Wait,
Yeah.
no. Wait. Okay.
Yeah, so this equation, so P is 5, is the number 5 an element of that set? Is it a rational number or not rational?
It's a rational number.
Yes, so you have to represent this 5 as a fraction, if you say so.
It would be 5 over 1.
Good, I'm very glad. So it's exactly 5 over 1. So it's P over Q. P is 5 and Q is 1, that's it. So therefore, you see, in the previous, so you see every single number n can be represented as n over 1. So therefore, n is a natural number, right, or integer, but also it's a fraction. So therefore, each integer is an element of rational numbers. So each integer is a rational number. Okay, a rational number, if you convert into decimal fraction, you will find two possibilities. For example, let me tell you. So, for example, if you take, so first of all, it could be an integer. Second, it could be, say, 1 over 2 is 0.5. It's a finite decimal fraction. Okay, finite. Now, if you take, say, 1 over 3 and look at the calculator and divide in column, you'll get 0.3333, and usually we just write 0.3 and then bar. By the way, in arithmetic proficiency test, when you have 1/6 or whatever, if you have periodic part, so it's period. Periodic part is 3. 3 repeats infinitely long. Okay, so you have to write this period and write bar. Okay, another interesting example is 1/7. It's 0.124857, and after that it will repeat 1, 2, 4, 8, 5, 7, da 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 da. So therefore, instead of writing infinitely many times, you just surround that period, write the bar, and erase the other part. Okay, this exactly means it's periodic. So you can say that a rational number is either finite decimal fraction or is a periodic infinite decimal. Okay, periodic, but periodic, infinite decimal fraction. But if I take square root of 2, for example, a number, so number, if you multiply by itself, you get 2. Okay, that number cannot be represented, it's not equal P over Q. Okay, when I teach mathematical majors, we prove that result. That result requires maybe half an hour to explain. It's very, very deep result. So square root of 2 is not an element of rational numbers. okay? But you can say that I'm wrong, because square root of 2 I can write in the same way as square root of 2 over 1. So it's a fraction. So it's a rational number. Is it true?
No.
Okay, what's wrong?
Well,
Okay, I represent this number as the ratio, as a fraction.
well, can it not be represented as a fraction if it's being divided by 2?
Okay, look here again.
Mm-hmm.
Fraction, and what's written for P? Integer. What's written for Q? Positive integer. If I look here, this is an integer, but this is not.
Okay,
You got it?
yeah, okay.
Both of them, both numerator and denominator must be an integer.
Mm-hmm.
So that's why, okay, but question is, maybe I can find such P and Q,
Mm-hmm.
so that square root of 2 equals that. It's a theorem, mathematical theorem, which says it's impossible. That's why it's not rational number. Okay, now I'm sick and tired of telling each time if this is an element of this is an element of that, and so on. Instead, we just introduce one more symbol. And that symbol substitutes the words element of a set. Okay, this okay, let me just try. So it's written on the page 7, designating sets. Page 7. Okay, when I say this set element is from that set, instead I can say this element belongs to that set. And there is a symbol. It's written like that. It means belong or belongs. Yeah, belongs. So if I use one element, it belongs. If many elements, that it belongs. So let me just write in parentheses, belongs to. Okay, got it? Now, it looks like an arrow, like this one. And arrow, if you raise this one, looks like inequality. And inequality came, just the designation of inequality came from the arrow. Arrow shows which one is smaller than the other. So if I write, say, 3 less than 5, yes, it's less. But if I write, say, 5, in the other direction, this will be greater than. So 3 less than 5, what's written in the sharp end of the arrows, okay, it's smaller. Likewise here. So the element belongs, let me just write, A belongs to A. So this is element, this one belongs to, and that one is a set. Okay, that one you have to understand exactly. So A belongs to A. A is an element of A. A belongs to A. Got it? And direction in that one, so it means that this one is kind of smaller than the whole set. It's only one element. For example, now let me give you some examples. So for example, 2 belongs to natural numbers. What does it mean? It means that 2 is an element of natural numbers, or it says that 2 is a natural number. Where? For example, okay, 7/8 belongs to Q. It's a rational number. Suppose I want to write that 5 belongs to N, and I don't want to rewrite it. What do I do? Darryl, listen to me. Okay, now it's important. I want to write that 5 belongs to N. So which direction I have to write? I write in that direction. You see, kind of 5 less than N. 5 belongs to that. Now, after that, I want to write that 1,000 belongs to, but I write it in here. I have to write this way. See, like an arrow. So 1,000 belongs to A. Got it? If I don't have enough room, so usually it's written that way. So 2 belongs to N, or you can write this way. If I write 2 belongs to n that way, usually in one line, but sometimes you can write a little bit inclined, okay? So you understand what is that? For example, 5, no, let's write, so suppose 6 belongs to the set 2n, right? Why? Because 6 equals 2 times 3. So therefore in this case n equals 3. It's 2 times n. And n is 3. I put in 3 and I get 6. So 6 belongs to that set. But if I write 5 belongs to 2n, it's not true. And then I cross it, like inequality. So in other words, you can say in words, 6, if 6 belongs to that set, it means that 6 is even number. 5 does not belong to this set. This set is the set of all even numbers. So 5 is not an even number. Okay, you got it. Yeah, for example, a simple example here shows, just erase. You see, it's a very, so far it's very unusual mathematics. It's kind of a new language. It's simple language, but it's a new language for the beginners. Okay, so suppose I consider the set here, 1, 2, 3, 4. Okay. Okay, now I just write the following. 2, does 2 belong to A or not? Is it true? Is that true?
Yes.
Yes, okay. True. It will be also questions like that. True or false? Okay, 3 belongs to A. True.
Okay, I get it. But
You
if
got
you
it?
said like 6 belongs to A, that would be false, because there's no
Good,
6.
very nice. Let me just write down. 6 belongs to A. False. Or how to write, so if I want to use A and 6, but the answer should be true. What should I write here?
The same, the belongs to, but you angle it to 6.
No,
Right.
it belongs but doesn't belong.
Ah, okay.
You see?
Okay. Okay.
Very simple, very simple. 6 does not belong to A. And 5 does not belong, so 1/7 does not belong.
Uh-huh.
How about this one? Okay, is it true or false?
False.
How come?
That's the set of no numbers.
Yes, of no elements. This set doesn't have an element. So 3 is not an element of empty set.
Right.
So that's why it's false. Or you can write 3 does not belong to empty set. It's true. How about that one? It's a tricky question. Okay, true or false? Okay, that is a tricky question.
So basically you're asking the null set belongs to.
Yeah, null set, it's also null set, but it's better to pronounce empty set. Okay, whatever you want.
Empty set, okay.
Yes.
That-
Does empty set belong to empty set? Or it doesn't?
No.
You
False.
say, and Shane, what do you say?
No.
No, okay, so false. Okay, why? Because empty set has no elements.
Right.
And if I write that something, this is an object, a new object. If this element, if that object belongs to empty set, it means that empty set has this object as an element, but it doesn't.
Right.
So therefore it's false, you're right. But what if I write the following? Empty set belongs to this. Is this true or false? You see, what's the difference? Here I didn't write parentheses, here I wrote parentheses. Okay, let's look what it means.
Well then,
Okay.
doesn't the empty set now become an element because?
Yeah,
these-
okay, let's look what is that. This is a set
Mhm.
whose one element, so it's in listing form. This is a set whose element, one element, is empty set.
Mm-hmm.
And empty set is written, it's an element of this set. So this is true. You got it?
Mhm.
So you have to you have to see this element inside that set.
Okay.
So therefore, okay, maybe just I frame that for a second. Empty set is not an element of empty set because empty set doesn't have any elements, and this set has one element, which is very strange element. This element is a set, okay, which is empty set. Okay, and maybe more. How about this one? 1, 2, 3 belongs to 1, 2, 3, 4. Okay, let me just write without that. So 1, 2, 3 belongs to 1, 2, 3, 4. It's true or false?
It's true.
Okay, look, 1 belongs to that. It's in here. You can find it here.
Yeah.
2 is in here, and 3 is in here. So it's true. But now let me write parentheses. 1, 2, 3 belongs to 1, 2, 3, 4. Is
Then
it true or false?
It would be false.
How come?
Because now that's a completely different set.
Yes, it's not a set. It's a set, right? But this is one object.
Right, okay.
And this object is not in here.
Right,
Because here is only numbers 1, 2, 3, 4, not a set.
right.
So therefore it's false. Now I ask you one more question. 1, 2, 3 belongs to 1, 2, 3, and then 4. You see I wrote parentheses here. True or false?
True.
Yes, true. Why? Because this is one object, and this is the same object. So this is an element of that set.
Oh,
Got
okay,
it?
I get, okay.
You got it?
I
By
get
the way,
it.
what is the cardinality of this set? How many elements does this set have?
2.
2. 1, and that is 2, not 4.
Okay.
That one has 4.
Okay.
Okay?
I got it.
So comma just separates elements, and this comma, you see, they're different. That set has 3.
Mm-hmm.
Cardinality is 3, but that set, it's a very strange set. One element is a set, and another element is a number. And you have only 2 objects, a set and a number. So therefore the cardinality of this set is 2. And that object is in here. So therefore this object is an element of that set. So it's true.
Well, that makes sense. It's just.
Makes sense?
Yeah, it makes sense.
So you have to be careful. You have to look. And say this one. Now, question, much more trickier question, is that one. How about empty set belongs to? Oh no, it's a little bit different. Yeah. Okay, maybe this one. Does it belong to the set 1, 2, 3?
Yeah, ooh, hold on.
Yeah, it's a tricky question, but not as tricky. You'll see later on, a little bit later, we'll consider subsets, and it will be more difficult.
It
Okay, look,
does.
what are the elements of this set?
1,
1,
3.
2, and 3.
Yes.
So what is the cardinality of this set? 3.
3.
1, 2, 3. And now let's look. This is an object.
Right.
Is this object among these 3 elements?
No.
No. So therefore it's U cross. Okay, okay, got it. It's that one is tricky question. Okay, so set numbers. Okay, cardinality is on page 10. You see, I did this a little bit different way. Okay, if you look at page 11. Let's make some small exercises on page 11. So K, so consider the following. K is the set A, L, G, E, BR. What is the word if you read it? Algebra, not algebra. Okay, I need to say immediately right now. Suppose I write A here. You see, so A is an element, L is an element, G, E, B, R, and A is an element. But we said already this A is an element. So therefore, if I write this one, it is the same as if I without it. If I write many objects of the same form, so A, L, 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 G, 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 it is the same. So you have to remove all of them. So A is an element. In the end, if I write A is an element, but I already just said so, it's called, that is set. Unlike set, there is a so-called multi-set, but we'll not use it. Multi-set when one letter is counted with multiplicity several times. But you see, so therefore you can write, it concerns which sets are equal. So this is the same set as A, maybe this one, L, G, B, R, A. So this is the same, because that element is counted twice. Only one time you have to use. Okay, so first, so this is B, M is that one, and C is empty set. Now question, find, so A, what is n of k? Now you can do this quickly. So what is n of k?
6.
6. 1, 2, 3, 4, 5, 6. But if you look here, you'll see 1, 2, 3, 4, 5, 6, 7. Be careful. I asked you that question, what is the cardinality of this set? If you write 7, it will be incorrect.
Okay, let me write that down.
Yeah?
Well, if the letter is repeated, then it doesn't need to be.
Not letter or whatever element. So if some elements repeat, therefore you have to eliminate all repeated elements first, and then count only the one element is counted exactly once. Got it? So therefore it's 6. Now B. What is n of n? 1. And C?
0.
N of empty set. Very good. True. And if you look in here on page 11, you will see the same answer. Okay. By the way, so let me just write one more. D. No. Suppose P. P is the following set: empty set, then this set, and then set and empty set. You see? You see, that is tricky question. So what is cardinality of P?
2.
2?
Oh, I know.
So what are the elements? Is this an element?
Yeah.
Yes.
Yes.
First element is an empty set. What's the next?
Oh, you're right. It is 3. It's 3.
Yeah, next element is a set whose one element is empty set. You see?
Right.
And this is a set which has 2 elements. One element is empty set and the other one is
Yeah.
set, one element of which is an empty set. So cardinality of this is 0.
Right.
Cardinality of this is 1. Cardinality of this is 2.
Yeah.
But you have here only 3 elements, not only but 3 elements, so the answer is 3.
Yeah.
Okay, that is tricky question, it's just for...
Yeah, but no, I get it. Yeah.
You got it?
3.
How about this one? Let me just ask question related to that. Empty set, does it belong to P? Or not?
Yeah,
It does.
Does? Why?
it's one of the elements.
Because it's an element, you see here. What does it say? It says empty set is an element of P, and you see it here. So it's an element.
But if it had the parentheses around it, it wouldn't be.
No.
Okay, how about this one?
Two.
How?
Because it's second element, second set.
Oh, okay.
You see, they are different. This element and that element are different. This is set empty, and this is set.
I see. It would just have one. Okay.
Yes, it's a different set. It's different object.
I get it.
Okay, how about this one? 0 belongs to P.
No.
This number 0.
No.
No, you don't see
Because there
0.
are no
So,
elements.
correct. And how about letter O? Belongs to P?
No.
No letter O. You got this, all of them look alike.
Mm-hmm.
Okay, let's consider the E. Set, call it O, which consists of elements 0 and letter O. So this one is 0, and this is letter of the same size. Maybe a little bit. Okay, letter. So 0 and letter. 0 and letter, they look like, but they are actually different. It's, you have to distinguish them. If you know that, they have to distinguish. So the cardinality of that set is 2, because it has 2 elements.
Mm-hmm.
And 0 is not the same as O. Okay, 0 is in here. 0 is a digit, and letter is that one. But you see, it happened once. I was in the hotel, and I wanted to connect with Wi-Fi, and it turns out that the password consisted of 1 and then 14 zeros. And no one was able to make this password, because if you click on 0, 0, 0, 0 14 times, eventually you just will lose. And if some of them are O's, not zeros, then it will be absolutely impossible problem to make a password. So usually that's why we have mistakes if you consider 0 as O and O as 0. Okay, got it. So now you understand. So that example is very important. So number 12. Okay, so designating of infinite sets, we'll talk about this one. Now, very important thing. Which two sets are equal? I actually said a little bit, but now I want to specify. So let me just write first. Set A equals set B if each element of A belongs P and each element of B belongs A. Okay, let me just write in logical without words. So if A belongs A, we conclude that A belongs B. Now if B belongs B, then we conclude that B belongs A. So suppose both conditions happen. If A belongs to A, okay, we look in the set B and we see that A is also in there. Suppose this happens. Take some element of B and look if it belongs to A. Suppose it also happens. If both of them are if this happened and that happened, let me just write here and. Okay, both conditions happened. Then we conclude that A equals B. Okay, it looks like very difficult diagram, but it's actually very easy. And now examples. So first example, consider the set A, B, C, D, and the set. So this set A, and another set is B, A, B, C, and this set is B. Are they equal or not?
Yes. Because
Okay, explain why.
they all have the same elements, just in different
Order.
Different order.
Different. Yes, exactly. A is here, so it's in here. You see, A belongs to A, so A belongs to B. Now B is in A, and it's in here. Each element in here is in there. But now let's go backwards. Each element in here is in there.
Mm-hmm.
So it's the only difference could be is the order. So let me just write order is not important. Okay, that is the feature. Maybe I just write 3 exclamation sign. No important. The order is not important. Okay, so if you have a deck of cards and then shuffle it, you have the same set of cards.
This,
The same set, because the elements didn't disappear, okay, didn't come back, so the same, so order is different. You see? So the set is the same. So if you put the cards in one line, it will be set. If you put in different, it will be the same set all the time. But the question, how many different rearrangements, it's a different story, which we'll learn maybe in November. That is the next, it's called combinatorics. Okay, it's a different chapter. But now what you have to say this one. How about this one? What if I write, say, A again, C again, C again, and B again? Are they equal or not?
yes.
Because look, by definition, A, B, C, D from the first set, all of them are here.
It would still go on.
Yes, now if I take every single element from here, it will be there as well.
Mm-hmm.
That explains why you do not need to write the same letter many times. Okay, so because it is the same as that one. Okay, so it's B. So B, A, B, C. So each element in here is in there, each element in here is in there. So that's it. Okay, now how about, you understand that? Okay, let me just try to give you another example, which also on page 15. Okay, B. Okay, you have set A is 2, 4, 6, and set B is X, such that X equals even number. Okay, are the sets equal or not? Okay, let's look. 2 from A.
Yeah.
Does it belong to B? Okay, look, so what is X's even number?
Oh,
So
yes.
2, so therefore it's even. So therefore 2 belongs to A, so let's write 2 belongs to A, 2 belongs to B. So far so good. Now 4 belongs to A, 4 belongs to B. Good. And the same for 6. 6 belongs to A, 6 belongs to A, 6 belongs to B.
Wouldn't B keep going infinitely though?
Yeah, okay, good. But if you take, for example, some other even number, say 100. 100 is in here, but not there. So it's not here, right? It will be just only a part. So that's actually cardinality of B is infinite, and cardinality of A is, what is that?
3.
Three,
There,
up
there?
to 6.
Yeah, good. I want to check, so if you understand. So this is finite set, this is infinite set. Finite set cannot be equal to infinite set. So cardinality is a property that distinguishes between infinite sets and finite sets. Now, if you have, for example, one set with 5 elements, another set with 7 elements, can they be equal or not?
I'm sorry, say that one more time.
Okay, set A has 5 elements.
Right.
Cardinality is 5, right?
Okay.
Set B has 7 elements.
Right.
Question, can A equal to B?
No.
No, because you see, first of all, we have to eliminate all repeated elements. Okay, cardinality means each element appears only once, and if it has 5 elements, they could belong to that set, each one. But 7 elements never could belong to the smaller set. So
Right.
that set is smaller. For example, you have 5 people and 7 chairs. Okay, so people could sit at 5 chairs, and 2 chairs will be Actually, it's a little bit different example. So chair is not a person. So these two sets cannot be comparable. Cannot be comparable because of cardinality. Okay, good. Okay, so we finished chapter 2.1, symbols and terminology. Next part is Venn diagrams and subsets, and I think we have to stop right now. Next time I will tell you what is Venn diagrams and subsets. So we have, okay, that's it, finished.